Here we go with the nervous system, port 2. We'll start with the port 1, and let's have some notes that we have covered in the port 1. You have to know that the group of nerve fibers, they give in urine, the group of neurons, they give a nerve, and the group of nerves, they compose what's known by the nervous system. Neurons are classified according to two criteria, their structure and their function. According to their structure, we have unipolar neuron, T-shaped one. This type is usually found in the sensory neurons of the spinal cord, one axon, one dendrite directly joined. Bipolar, usually found in the retina of the eye and the cerebellum, one axon, one dendrite joined to the soma. Multipolar, found in the cerebral cortex, retina, the spinal cord, many dendrite, yet still one axon, always leave the cell body. According to their function, we have three. We have the sensory neuron, we call it afferent, receives and conducts sensory information from the peripheral sensory organ to the central nervous system. Second type of neuron is called associative neuron. It's called the interneuron, receives nervous messages from the sensory neuron, integrate it, analyze it, and then they send the message to the motor neuron. It's like a link. It's called associative or interneuron. Mainly, is found in the brain and the spinal cord. Motor neuron is called efferent neuron. It carries nervous messages away from the central nervous system toward the effector organ, whether a gland or a muscle, to induce a response there. So according to their function, we have three main neurons: sensory, which is called afferent, interneuron, or it's called associative neuron, and the motor neuron, which is the efferent neuron. Okay, so let's move now to the structure of the neuron. This is the myelin shaft. We said that the myelin is a lipoprotein that has an insulator role, and it has a role in acceleration of the nervous message. Why? Because in the myelinated axon, the message will move in a saltatory manner, will jump over the myelin shaft. So it moves like a saltatory manner by jumping over the myelin shaft between the gaps. These gaps, they are named as node of Ranvier. Actions. We have two different actions. Either we have voluntary actions or we have the involuntary, which are called the reflexes. Voluntary actions, the action that require thinking, while the involuntary, that are called reflexes, that do not require thinking. Action that require the intervention of the brain in addition to the spinal cord, we call them voluntary, and action that do not require the intervention of the brain, we call them reflexes. Factors that affect the speed of the propagation of the nervous message. First, we have the diameter. As the diameter increases, the propagation speed of the nervous message will increase as well. Myelination. Presence of myelin has higher effect on the increasing the speed than the effect of the diameter. So myelin is an insulator. It acts like an insulator. It doesn't conduct a nervous message, otherwise it allows the message to move faster by jumping. This is called the saltatory manner movement. Aim of the following experiment is to study the electrical state of a neuron at rest. Okay, let's start first with experiment 1. Experiment number 1, the needles of the voltmeter, they are found on the external side of the axon, on the external medium or on the surface of the axon. So the voltmeter indicates 0, and the oscilloscope shows 0 millivolt, which is potential difference, delta V. So the needle of the voltmeter didn't deviate from 0. What does this imply? This means that there is no potential difference across the surface of the axon, or we can say that there is no potential at all at the surface of the axon. In experiment 2, we placed the needles of the voltmeter inside, on the internal side, on the interior of the axon. So there is no potential difference, delta V is equal to 0, and the voltmeter didn't deviate. Why? There is no potential difference across the surface of the axon or the axon itself. While if we put the needles of the voltmeter, one on the internal side and the second on the external side, the needle of the voltmeter deviate away from 0 and move to the minus 70 millivolt as shown in the oscilloscope. So what can we deduce here? First, you have to know that a neuron at rest. You have to know that there is exists a potential difference between the interior of the axon and the exterior. So interior and the exterior, we have a potential difference. So delta V does not equal to zero. So this nerve fiber is said to be polarized. Since it's negative, so polarized means that it's negatively charged. Since it's negatively charged, meaning that the interior of the nerve fiber, the internal part of the nerve fiber, is negatively charged compared with the external part. You have to know that as a note, that the resting potential is the potential difference. Whenever I said resting potential, it's the potential difference, it's delta V, that exists between the intracellular and the extracellular, internal and external side of a nerve fiber, but we're at rest. So this is an important note. You have to know that the resting potential, it's the potential difference that exists between the internal and the external medium of a nerve fiber were at rest. Okay? So the resting potential, there is an electric charge across the membrane. This is called membrane potential. The resting potential, meaning that when the cell is not firing, meaning that when the cell is not active, it's at rest. It's 70 millivolt, minus 70 millivolts for sure, between the internal and the external. So the resting potential is the potential that exists. You have to know it. The potential difference that exists between the internal and the external media of a nerve fiber were at rest. Okay, that's why it's called resting potential. And you have to know that we have potential difference between the internal and the external nerve fiber. Delta V does not equal to zero. So the nerve fiber is said to be polarized. It's negatively charged. You have to know that all cells, not only the excitable cells, they have resting potential. So it's a potential difference between the internal and the external. Resting potential is not always minus 70 millivolt. It ranges between minus 5 to minus 90, depending on the species and the nature of the nerve. Different species, they have different resting potential. Ions and resting potential. Ions, you know that we have anions and cations. Cations, they are positively charged, whereas anions, they are negatively charged. So ions, they are electrically charged molecules. Either they have positive charge like sodium ion, potassium, magnesium, for example, or negatively charged like chloride, let's say, for example, chloride ion Cl minus. We have also, let's say, negatively charged chloride ions. We have also, let's say, negatively charged ions, oxide, O2 minus, and so on. So the resting potential exists between ions. They are concentrated on different sides of the membrane. Na plus and Cl minus, they are presented outside the cell, whereas K plus and other organic anions, they are found inside the cell. Let's have here a look about the ionic relation in the cell. A concentration of Na plus outside the cell is sometimes 10 times greater than inside. You see here, cytosol means that in the cytoplasm, okay? And extracellular fluid in the external side, or outside the cell. Outside the cell, the concentration is 150 millimolar, while in the cytosol it's 15. It's about 10 times greater. While inside the cytosol, concentration of K plus is 150, while that in the external it's 5, about 30 times greater. Cl minus it's 10, while outside in the extracellular media it's about 120, 12 times greater. So the question here, what is the origin of the resting potential? Origin of the resting potential, we have differences in the ionic distribution. We have difference in the distribution of ions between the internal and the external side of a nerve fiber. This is the first. Second, we have difference in membrane permeability. For example, we have channels. We have permeability for ions. We have channels that allow the entrance of, for example, Na plus and the exit of K plus. This is called a pump. We said this the last time. It's called Na plus K plus pump. For example, this permeability, membrane permeability is more permeable to potassium than to sodium. This will lead to the appearance of the resting potential. This will lead to create an electric current across the membrane, which the origin of the potential difference. So the origin of the resting potential, difference in the concentration of the ions, and difference in the membrane permeability for the different ions. Here, if you have a look for this, let's have a look for this figure. Here, 3 Na plus, they are picked, and then 3 Na plus move outside of the cell, and 2K plus they enter inside the cell. So 3 Na plus, they are pumped to the extracellular fluid, and 2K plus they are picked, meaning that we lost one positively charged. We have 3, 2 entered, and 3 goes outside, so we lost one positive charge. Okay? ATP is the source of energy. It's called adenosine triphosphate. Okay? So 2K plus are pumped into the cytosol, where we have, in the beginning, we have 3 Na plus. Let's repeat this. Let's repeat this at the beginning. At the beginning, you have 3 Na plus in the cytosol. They move to the positions where they are bound. So 3 Na plus were enter inside the cell, and then 2K plus enter, and 3 Na plus they go to the extracellular fluid, and we have 2K plus. So K plus 2, here we have 3. So we have 3 positive and we got 2 positive, meaning that we lost 1 positive. And by this time, according 100 of time, we will move to the negatively charged medium. Okay? So the membrane is more permeable to K than Na plus, thus the inside will become more negative. Okay? Allow the enters of K plus and allow the exits of Na plus. So Na plus go to the outside, K plus enter to the inside. This will make it more permeable, and thus the inside will be more negative. Okay? How is the resting potential obtained or maintained? Due to differences in the membrane permeability to sodium and potassium ions. So we have permeability for K plus more than to Na due to the difference in the concentration of the ions between the internal and the external, and we have the action of sodium potassium pump, Na plus K plus pump, allowing the exit of Na plus and the entries of K plus. Okay, it's called Na plus K plus pump. To keep in mind some notes, you have to note them. First, excitable urine. What is an excitable urine? Excitable urine is a urine that's able to respond to an effective stimulus. Effective stimulus, next week we're going to talk about this in details, is the stimulus that causes the appearance of an action potential. It leads to the action potential. For example, I hit your face, I slap you in the face, for example. First time you didn't feel. Second time you didn't feel. Third one, you feel hot. You feel it very good. So this third one is called effective stimulus because you have an action potential when this slap. Okay? Action potential. Action potential. You saw, for example, in the electrocardiogram, whenever you did a heart, for example, heartbeat analysis, electrocardiogram, it shows these graphs. So these graphs that moves up and down for the heart, for example, these are called action potential. It's the term given to the electrical visualization of the response of a neuron. Also, the threshold of excitation. What's the meaning of threshold? Threshold of excitation is the minimum intensity, is the minimum strength of a stimulus that's able to stimulate or emit a nerve impulse. For example, this laptop or this phone, for example, it needs electricity of about 220 volt. Below 220, it won't work. Above it, it works normally. So the threshold is 220 millivolt. Okay. Below this, in the case of nervous system, below it, there is no action potential. Okay. Upon excitation, a change in the potential difference across the interior and the exterior of the nerve fiber should occur to reach the threshold of depolarization and to initiate an action potential. What is the threshold of depolarization? Is the minimum change in the potential difference to cause an action potential. It's called the threshold of depolarization. These notes, you have to know them and you have to study them before we move into more complex ideas. Minimum time of excitation. Minimum time of excitation is the minimum time during which an effective stimulus should be applied to excite a neuron to have an action potential. It's called minimum time of excitation. The action potential in a nerve fiber. First, the resting potential, as you know, it's minus 70 millivolt. Already we know this. Upon application of stimulus I1, I1 intensity 1, it's less than the threshold of excitation. It's less than the minimum value. So here, no change in the potential difference, as if nothing occurred. So as such, the stimulus is said to be ineffective stimulus. Why? Because it doesn't cause the appearance of an action potential. Second one, we applied stimulus I2, less than the threshold, but I2 it's greater than I1. So we have here a small action potential. This is referred to as, it's called artifact, okay, or it's called hypopolarization. So here, threshold of the polarization, we didn't reach it. So slight change in the potential difference. It's called hypopolarization, or it's referred to as artifact. It didn't reach the threshold of depolarization, then everything will go back to the normal and goes to the resting state. As such, the stimulus is said to be ineffective. Here we did a stimulus of intensity I3. I3 is greater than or equal the threshold of excitation. So I3 is greater than I2. So here we have an action potential which moved to about plus 50 millivolt. So here an action potential occurred. So the first intensity to cause the appearance of the action potential, we call it the threshold of excitation. Okay, so it's called the threshold of excitation. This is the action potential is found here. So recording of the action potential, here we have the stimulating electrodes, and we have a recording electrode, which is a reference, which is found in the ground, and here we have the recording on the oscilloscope. This is like the one shown in the electrocardiogram. Whenever you did, for example, or you saw somebody in the emergency room, for example, to use the electrocardiogram to find out the beating of the heart and the waves. So this is called an action potential. Whenever it becomes null, meaning that bye-bye, it's dead. Okay? So upon application of a stimulus of intensity I3, I3 it's greater than the threshold, as we said. So enough change in the potential difference, enough change in the delta V that reaches the threshold of depolarization. So we have an action potential of amplitude 120 millivolt. Why it's 120 millivolt? Why? Because we move from minus 70 to plus 50. So minus 70 to plus 50, if we want to make between, for example, absolute value, so it's 70 plus 50, we move about 120 millivolt. Okay, guys? So it's a 120 millivolt action potential. So the intensity is said to be effective. And since it's the first intensity or the first stimulus to cause the appearance of the action potential, so we call it the threshold of excitation. I4 greater than the threshold. I4 is greater than I3. So we have also an action potential. So I4 is said to call the effective stimulation since it causes the appearance of the action potential. So as a conclusion, the stimulus that doesn't cause the appearance of the action potential, we call it ineffective. The first one to cause the appearance of an action potential, thank you, Mr. Ali. The first one to cause the appearance of the action potential, we call it the threshold of excitation, and the one that causes the appearance above the threshold of excitation, above the threshold of excitation, we call it effective stimulation. Okay, this graph is showing the different phases of the action potential, number 1, number 2, number 3, 4, 5, 6, and 7. These you have to study them. Next week, our work is going to be related to this graph, which shows the phases of the action potential. So during the phase of the action potential, we have phase number 1, it's called the resting state, where it's minus 70 millivolt. 2, it's called the artifact, or it's called the hypopolarization. What the meaning of polarization? negativity. Hypo, it's decrease or less. So hypopolarization, it's decrease in the negative. We are moving to the positive. Three, depolarization. Number four, inversion of polarity. Number five, which called the repolarization, going back to the negative. Number six, we move below the resting state, meaning that we move less negative, less positive, meaning that more negative. We move down, minus 80 or minus 90, meaning that's called hyperpolarization, meaning that highly negative. Hyper, for example, I said Mr. Muhammad is hyper in the session, so it's very active. Hyperactive is very active. Hyperpolarization, very negative. And number seven, it's called returning to the resting state. So this slide is showing the different phases. Resting potential, number one. Number two, it's called hypopolarization artifact. Number three, depolarization. Number four, inversion of polarity, meaning that the change from positive to negative. Repolarization, going back to the negative. Hyperpolarization, moving to the negative in extreme way, very negative. Hyper, below the threshold, meaning that threshold it's minus 70, move to minus 80 or minus 90 millivolt. And number seven, returning to the resting stage. This graph is going to be our new lecture, lecture number three, related to the nervous system next week. So this graph is very important, and we will talk about this graph in details next week. Okay?